Hey you guys, John Britt here. Hey, we're going to start our next section on understanding glazes. And so what I'm going to do here today is ambitious as always, and I'm by myself as usual, no friends. So what I'm going to do is we're going to go through the unity molecular again real quickly, and then what we're going to do is describe properties of the oxides, because that's one of the most important things for you to know how to do, or to remember all of the things that say sodium would do. So when you see a high sodium glaze, you can predict what it will do, what behavior it will have. Okay, so first of all, this is our flux column, and here's our alkaline fluxes, our alkaline earth fluxes, our metals, got our refractory, and we got our glass former silica. Okay, so now over here I've got opacifiers and colorants also, and some miscellaneous things. What I'm going to do, since this will be impossible to do in very fast because each one takes a while, each one you could write a book on, let's put it that way. And so we're just going to try to do 1 or 2 minutes on each one. And then what you should do is really read in the book what these properties are and try to memorize it yourself. Even if you don't memorize it, familiarize yourself with it. So in my book on page 19 to 21, I have a description of the properties of oxides. So in this case, we're going to be talking about melting point, coefficient of expansion, surface tension, viscosity, volatilization, toxicity, color response, sources, and mesh size. So all those are described on those 2 pages, 2 or 3 pages. And then if you continue on from 21 to 31, I've got a description of each oxide, and I have multiple paragraphs about each one. And remember, this is just a general overview. Because if you want to get really precise about this, like I said, you could write an entire book. People have done massive papers on these things, and we're just doing some highlights so you get an understanding. I don't think you need to know everything about all these oxides to make pottery glazes. It just helps you to look at a recipe and understand, oh, nepheline cyanide, that's a source of sodium, feldspar. That might create glazes that craze or hard pan, etc. Okay? So that's what we're going to do. I guess we'll just start in with sodium. I have this written here, and I'll write them up there, and then maybe you can just take a glance at it at the end, or screen save or something, so you can follow along, because I'll be going pretty quick. So this melts at 1652. Now, that's not that important to know in general in ceramics, the melting point, because eutectics are formed. And that's a combination of oxides which will make the melting point lower than all the melting points of the constituents in there, because they combine together to create a lower melting point. But some things you want to know, like say for instance, if you did soda ash glazes and you needed to start reduction early before the sodium melted, you would start before 1652, which is about cone 012. Okay, that's why people start early, because then there gets soot on there and the sodium melts and traps the carbon. It's called carbon trapping. Okay, so then sodium has a high coefficient of expansion, and what that means is that it could cause crazing. It has a low surface tension. Surface tension, just in case you don't know, is when a bead of water will be on a piece of glass. And I'm sorry, when water is on glass, it will bead up because the water has a high surface tension. Okay, same thing with glazes. What that may mean to you is that it may cause crawling. Because if it gets on your glaze and there's any irregularities or discrepancies in the coat, then it will, instead of flowing over it and healing itself, it'll bead up into crawl spots. Okay? It has a low viscosity. Viscosity is thickness, like honey. It does volatilize. It goes off as a gas at about 2012 or something. It'll start going off as a gas, and that's how we do soda firing and salt firing, because of the property of sodium going off as a gas. Volatilization is like when water is heated up, it volatilizes as steam. When sodium heats up, it will volatilize also, and many other things like copper, chrome, lead, and so we'll go zinc, and we'll go through many of these and tell you, okay? This is not really that toxic. It has a bright color response. And so, so the one thing you would know about sodium is it could cause crazing, makes brightly colored glazes, melts very low. Because remember, the thing I'm comparing it to is silica, which melts at 3110 Fahrenheit. So that's pretty high, and this melts at 1650. Okay, the sources, whenever we get sources of materials, we never get sodium oxide. That's explosive. But we'll get it as a sodium carbonate, or we'll get it as a feldspar. And so that's what you need to know. And some sources have different mesh sizes, so you may choose a finer mesh size or a coarser mesh size depending on what you're doing. Okay, so the soluble source would be sodium carbonate. The insoluble source, that means it doesn't go into solution in the glaze bucket, it's going to be soda feldspar. So there's many types of feldspars. Well, many types of sodium feldspars. Like the main one is going to be Minspar or Nefsi. And then other ones, in the olden days, we had NC4 and we had F4. And then also remember this, that feldspars, you can't separate out the sodium and the potassium, so we often talk about them together. And so say Minspar is not all sodium as the flux, it's got sodium and potassium, and we'll often write that as KNaO. Okay? So that might be our first one, which we did. Now we're going to do, see how my eraser works. Now I should have mainly left all those up there because sodium and potassium are very similar. So this melts at 1382 Fahrenheit. And so that's very low. It's got a high coefficient of expansion, may cause crazing, low surface tension, low viscosity, does not volatilize like sodium, not really that toxic, bright glazes. Okay, and then the source of that would be potassium feldspar. Custer spar is the main potassium feldspar. Other ones might be Mahavar feldspar, G200HP, G200EU. Well, you can also get it in like Cornwall, plastic Vitrox. These are other sources of potassium. And the soluble source is potassium carbonate, pearl ash. Okay, one of the main nice things about potassium, it makes nice copper blue reduction, copper blue glazes. Okay, I forgot to tell you some things about sodium. You can use sodium because it's soluble, I said, in a carbon trap and also in Egyptian paste, because it'll come to the surface and deposit it on the surface and make it's called a self-glazing clay. Okay? Of course, as you know, there's no way for me to remember all this stuff and tell it to you in a short period of time. That's why I have the workshops and stuff. We lengthen it a little bit. But you're going to be reading in that book, and I've got all of the things in there that I just forgot to say. And also remember, you can go on to Tony Hansen's site, Digital Fire. Just Google sodium oxide properties, Digital Fire. Up will come all kinds of stuff. And the beauty of Tony's website is that he updates it all the time, and it fixes things and adds things he learns, etc. All right? So let's do our next one. This will be called lithium. And that melts very low. That melts at 1472. Okay, and then the overview of this, it's the lightest and smallest and strongest of all the alkaline fluxes. So here's our alkaline fluxes. It has a low coefficient of expansion. That means it can cause shivering. So sometimes when you have spodumene or lithium carbonate glaze, they can cause shivering. That's where the glaze sheets off instead of, it's the opposite of crazing. Another, though, advantage of that being low, say you had a high sodium glaze and it crazed, and then if you added some spodumene that's high in lithium, maybe those two would counteract each other and you could cure your crazing problem by doing that. Okay, it has a low surface tension, low viscosity, does not volatilize, somewhat toxic. Some people who are on lithium medication do not want any more lithium because they're at a certain level, and so they don't like to be around any lithium or have lithium in glazes. As long as your glazes have a high enough silica and alumina, they won't leach anyway, but some people are concerned about it, so that's why I write yes. It's bright glazes, and the sources are going to be, insoluble source is going to be lithium feldspar like spodumene or petalite, and the soluble source would be lithium carbonate. That's the pure source. Okay? So 1 to 2% of lithium carbonate in your glaze could drop at one cone in melting. That's how strong of a flux it is. All right, we did that. Now what we need to do is to do calcium. Super good material for glazes. It's in almost all glazes at all temperatures. It makes strong glazes, great for functional glazes like celadons and stuff. It makes strong surfaces. Okay, its melting point is very hot. But it forms a eutectic with alumina and silica, which is the classic eutectic in ceramics, which brings it down to about 2100 to melt. So that's super good. It has a high coefficient of expansion, high surface tension, medium viscosity. Now, the reason that has a high surface tension, or the application of that high surface tension, is when you have high calcium glazes, you can get ash glazes, which form rivulets. So even though they're very runny, the fact that they pull together and form these it looks like tree branches or tributaries from above, ash glazes, and that's because it's pulling in, its high surface tension is having it pull together. It does not volatilize, it's not very toxic. It has a moderate color response. What I'm saying about this is that sometimes people say it bleaches iron, so in ash glazes even, or celadons, it'll slightly make the iron a different color, a lighter color that people like in blue celadons or blue-green celadons. Okay, the main source is going to be whiting. Another source is going to be dolomite or wollastonite. Those both contain calcium. And then the soluble source will be like bone ash, Gersley borate, ulixite, unwashed wood ash are all sources of calcium in glazes. All right, also, hopefully, I'm talking very fast, and sometimes I might say the wrong thing, so you've got to look this up and make sure that I'm saying the right thing. Okay, now we're going to talk about magnesium, and it melts at 5072 F. Magnesium oxide. It has a low coefficient of expansion, so oftentimes people will add, say, talc to a glaze because that's magnesium and silica, and that'll lower the expansion and stop their crazing. It's got a high surface tension, so cause crawling, a high viscosity, does not volatilize. It's not really toxic. It has a pastel color response. That means the colors that you get with high dolomite or high magnesium glazes will be pastel tones. And it makes pastel mattes is what we say usually. You know, it's not always the case. If you have a lot of magnesium or just a little, then you may not get mattes from it. It may help in the melting, but this is generally what people say about magnesium is pastel matte surfaces. All right, so the sources are going to be talc, dolomite, and magnesium carbonate. The soluble source would be Epsom salts, but you really don't use that in glazes. Okay, so I'm trying to think. Val Cushing used to love dolomite, magnesium glazes, so a lot of his glazes are in this category. All right, now we're going to do barium. And barium melts at 3493. It has a medium coefficient of expansion, a medium surface tension, high viscosity. It can produce stiff glazes. Does not volatilize. It's toxic as barium carbonate. As barium sulfate, it is not. Barium sulfate is what you take when you go to the doctor and they make you drink a quart of this stuff and take an x-ray. So it depends on the type or the source which is toxic. It makes bright matte glazes. That is significant because if you make glazes with matte glazes are often made by adding kaolin to a recipe or alumina to a recipe, and that makes dull glazes or kind of earthy. And so the fact that you can get bright matte glazes is super exciting for people. Its main source is going to be barium carbonate, and the insoluble source is barium sulfate. The interesting thing is Joshua Wedgwood, back in the 1780s or sometime around then, he made Wedgwood pottery, and he made his workers use barium sulfate so they didn't get toxic exposure, which was pretty good for that long ago. Okay, so let's do strontium now. So strontium melts around 4406. That's pretty hot also. It can start melting around 2100. See, all these things, even though we say an oxide has a melting point, what really is the case, we're getting it as strontium carbonate. And so when that heats up, it has to drive off the carbon dioxide. So that changes it. Same thing with all the other ones I just talked about. They all have a carbonate associated with them. And so you got to find out when that leaves, and then anyway, that affects the melting point. Okay, so what am I doing here? I'm going to write up here strontium. It melts there. It has a high coefficient of expansion, medium surface tension, medium viscosity, does not volatilize, no known toxicity. So that's good. It's a lot like barium, not exactly, but many colors are the same or similar. And so if you don't like the toxicity associated with barium, then you can substitute strontium. It's usually 0.75 strontium to 1 gram of barium. But that's not perfect. You just have to test and see, and you may not get it perfect anyway. You get it close though. Although people who like barium glazes don't like strontium. It's not exactly the same, and it has a certain surface quality that they're after that strontium doesn't produce. Okay, so it also makes bright mattes, especially with stuff like cobalt, copper. It's just spectacular colors. Okay, its main source is strontium carbonate. All right, I think we're doing okay here. We're going to do the best we can. We're going to do zinc now. So zinc, what they say with zinc, zinc makes ink. That means it makes dull colors, but really it should be zinc has a dramatic color response because it will, well, crystalline glazes are very bright and shiny, and they're 25% zinc in terms of the recipe. And so, but if you put zinc with chrome, you'll often get browns, which is what people don't like. So we say zinc has a dramatic color response. Okay, it melts at 3587, but around 758, I think, and you put it in reduction, the oxide will be driven off, and you'll have zinc the metal, and that boils at 758, and it goes off as a gas. So that's why people don't like zinc in reduction glazes. Okay, it has a low coefficient of expansion. It has a high surface tension because you can have zinc crawl glazes. It has a medium viscosity. I said it volatilizes. It can be toxic. If it goes off as a gas and the metal is in the air, it's not good. So you want to have your kilns vented, particularly, well, reduction kilns, either have them outside or vented well. It has a dramatic color response. And its sources are going to be zinc oxide. Now I will tell you this, if you're into zinc glazes, there's many sources of zinc. Dentox, Maximo 910, Cerox 506, Zoco 102 and 103, and I'm sure there's more that I don't know about. I just have recently tried to find some zincs, and they're all different. And so the problem is once you get going with a glaze testing cycle, and then all of a sudden you run out of your zinc, now you got to find the same source or something that you can continue to get regularly. Otherwise it changes your recipes a lot. Okay? So we did that, and then now we'll do lead. I don't really have a lot to say about lead because I don't use it, but you should at least know about it. It melts about 1652. It has, let's see what it has. It has a low coefficient of expansion, low surface tension, low viscosity, makes beautiful glazes, defect-free. That's why people like them, because they were fantastic. But it does volatilize, especially above cone 6, so 2232 about. It is toxic. That's the bad part. So in the olden days, people used to sift on galena, which is lead oxide, onto their pots, and they died about an average age of 25 or something because of breathing in the lead. So they started fritting it with silica. So it's called lead bisilicate, is a frit of lead that the user can't ingest it because it's tied up with silica, but the end user in the glaze, once it gets in a glaze, it'll melt and then be available to leach. So it's bad. I just saw a thing about Corelware because they have decals on there, and they've recommended that you don't use their decal stuff except for decorative pre-2005 or something. You Google that and see, but I know Duncan had some problem with lead glazes. In low fire, there's glazes called lead safe and lead free. Lead safe meant that if you fired it correctly, it would not leach except to acceptable limits. Lead free is what I recommend because what happens is many kilns under fire. And so people don't even know they're under fire. Maybe an element will go out. And so Duncan found out that a lot of their glazes were leaching. They had to discontinue them. This was back, I don't know, 2008 or something, a long time ago. Anyway, so the main source would be white lead or red lead. Those are soluble, and then frits or lead bisilicates are insoluble. Okay? I think we're doing pretty good. Let's see what else we got here. So we did all the fluxes there. Now we need to do boron. because boron, even though it looks like a refractory in structure, R2O3, it actually acts like a flux, and it is a glass former. So that's an excellent material. What it really does is it's not a really good flux. Say sodium will reduce the melting point of some glazes like about 1800 degrees, whereas boron will only reduce it 300. But what it does, so that's why they say it's an inefficient flux, but what it does is break silica bonds, and so that is a way that it gets things to melt better. So it melts at 1292. It has a high and a low coefficient of expansion. So in small quantities, it has a low coefficient of expansion and may stop crazing. In higher quantities, it may increase crazing. It's got a low surface tension, low viscosity. I don't think it volatilizes. Oh wait, yes, it does volatilize a little bit, but not as, it's not as bad as say zinc. If you did a melt test of zinc in oxidation and reduction, in reduction, the entire melt test would be gone, whereas in oxidation, it would be unmelted. So I think this volatilizes, but not that much. Let's see, it is not toxic. It has a bright color response. Its sources are Gersley borate, Fritz, ulixite. The soluble sources are borax. Okay? I think we're getting down here. I think what I'll do is do this phosphorus. We're going to stop after about 30 minutes. P2O5. This is in plant ash, and tricalcium phosphate or bone ash. Okay, it melts at 1072. Oh, whoops, that wasn't very good. It's also a glass former. It is a high coefficient of expansion, low surface tension, low viscosity, does not volatilize. It is somewhat toxic. It is the color response. What you usually use it for in ceramics is tomato reds, so khakis, persimmons, and chun, celadons. So they like to get a little bubbles and opacity from bone ash. And the sources are, so this is called colloidal opacity. The sources are going to be tricalcium phosphate, called TCP, that's synthetic bone ash, and Fritz. Okay? Let's see if we can swing in here alumina while we're at it. So alumina, that's our main refractory. That melts at 3722. It has a low coefficient of expansion, has the highest surface tension, and the highest viscosity. So that can cause crawling. So if you put kaolin, too much kaolin in a recipe, you can get crawling from shrinkage as it's drying or from the high surface tension. And it makes very thick glazes, or stiff. It does not volatilize, no toxicity. It's got dull colors, like I said before. That makes earthy, sort of not bright colors, put it that way. And the main source is going to be kaolin. The main source of a refractory in like kiln wash could be alumina hydrate or alumina oxide, but they cost $1 something a pound, whereas kaolin is like 20 cents a pound or something cheap. Also, feldspars contain alumina. Maybe that's enough for you. All right, let's do our last one here. We're going to do silica. Then we're going to take a break. You're going to go read, make sure I said everything right, and then see if there's more stuff in there that's helpful to you. Okay, so this has a high and a low coefficient of expansion. And what that means is as a crystal, it's got a high coefficient of expansion. That means it may cause crazing. Generally, in the body has a high coefficient of expansion if it's not melted. If it's melted, it's amorphous, and then it's got a low coefficient of expansion. So that could help stop crazing. Okay, so it's got a medium surface tension, medium viscosity, does not volatilize, is not toxic in the glaze, but in the dry state in a clay, it can be toxic as a dust, cause silicosis. So that's a dilemma with talking about toxicity, because you can't just say yes and no. It can make glazes very safe and very non-toxic, because if you have enough silica and enough alumina, it ties everything up and you have no leaching. But if you have a filthy studio with dust everywhere, then you may be breathing this in all the time and get silicosis, so super bad. So the source is going to be silica. There's types of silica, 200 mesh, 325. 325 is usually the standard. Nowadays, you get a lot of silica in rice hull ash. You can buy amorphous silica and add that to a glaze. Okay, I think we did it. Let's hope it looked good, and I'll do the next one hopefully tomorrow.